right, let's get started. My name is Greg Bovinger. I'm director of the National High Magnetic Field Laboratory, and it's my great pleasure to introduce two friends, Eric Betzig and Harold Hess. They'll be giving a tag team colloquium, and the reason is that they've worked together for so many years, first at Bell Laboratories and now at Genelia Farms, on improving and really revolutionizing microscopy, as you'll hear. So I'll first introduce Eric, who will give the first talk, and then Harold, and then Eric will wrap up at the end. Feel free to interrupt if you have questions, and then we'll take questions at the very end of all three talks together. So Eric was born in Ann Arbor, Michigan in 1960. He got his undergraduate degree in physics at Caltech in 1983 and went to Cornell, where he got his master's and PhD degree in applied and engineering physics in 1985 and 1988, respectively. After receiving his doctorate, he worked at AT&T Bell Laboratories on near-field scanning optical microscopy. And he left Bell Labs in 1996 to become Vice President of Research and Development at Ann Arbor Machine Company, which was owned by his father, where he developed a technology for adaptive hydraulic machining, and he'll be the first to tell you that that was not a commercial success. He then returned to the field of microscopy and developed photoactivated localization microscopy, or PALM, which is the reason that he was awarded the Nobel Prize in Chemistry in 2014. He developed that in the living room of his longtime friend Harold Hess, and in 2006 he joined Howard Hughes Medical Institute's Genelia Farms Research Campus as a group leader to work on developing super high-resolution fluorescent microscopy. As I said, Eric was awarded the 2014 Nobel Prize in Chemistry, and it's my great pleasure to present him to you today. Thank you.
Thanks, Greg, and thank you all for coming. I apologize in advance if anybody went to the first of these talks a half hour ago, because if so, you're going to have to hear the same lame jokes over again. So as many of you know, the wave nature of light sets a limit on how small of an object you can see in an optical microscope. So if this is the size of a protein molecule, then this is the size of the fuzzy ball of light that you would see from that molecule in a normal optical microscope. So this is a bit of a problem, because in my mind, one of the most interesting mysteries is how do you go from single molecules, which are a few nanometers big and are inanimate, and are produced stochastically inside of a cell in which there might be 100 billion such molecules, and by some magic, their emergent property, they manage to come together to create something which is animate, that lives, that reproduces, and furthermore, despite that stochasticness down here, is robust at this level of a cell under perturbation. How does that happen? It's crazy. And so what we need are tools to be able to connect molecular biology to cellular biology. And that's what a lot of my career has been about. So I got into this question back in '82 when I went to graduate school and met my advisors, Mike Isaacson and Aaron Lewis. Mike had developed a way by using e-beam lithography to create holes much smaller than the wavelength of light in an opaque screen. And he and Aaron reasoned that if you put one of these screens right up against the cell and illuminated one side with light, then the light that comes out of the hole would be initially confined to the size of the hole rather than the wavelength, to make a little nano flashlight that you could drive around point by point and get an image with the resolution of an electron microscope, but able to look at living cells. So we call this near-field scanning optical microscopy, or NSOM. So I worked on that technology for 6 years, got my thesis with some sort of results, but it was enough to get me in the door at Bell Labs with my own lab. In '88, I started working there, and the first 2 years were painful, because whenever you started as a new MTS at Bell, you always felt like a bit like you were on probation, because God damn it, this is the place where the laser and the transistor and all that stuff happen. I don't belong here. I'm not good enough, right? And so you felt very inferior, and the fact that my project wasn't succeeding that well just enforced that fact. But I had a lot of help because in my same department, I had another young MTS who arrived a few years before me, who's seated right here. That's Harold Hess, who quickly became my best friend and colleague ever since the late 80s. And so with Harold's encouragement, eventually things started to succeed with near field, made some technical innovations. At one time in 1992, we had the world record for data storage density, where we were able to write bits as small as 60 nanometers versus these sort of diffraction limited bits. We were able to do super resolution photolithography, study histological sections, and in 1993 I was the first person to do super resolution fluorescence imaging, where I was able to look at the actin cytoskeleton in fixed cells using the near field technique. So the other two experiments that actually proved influential for both Harold and I later on was in 1989, W.E. Morner at IBM Almaden, while he was working on a means of using spectral hole burning as a data storage device, was able to show eventually that he could detect the spectral signature of single molecules near absolute zero. And so it became that captured the imagination of many people and became a prime goal to see if you could see and image single molecules at room temperature. The problem wasn't so much the amount of light a single molecule would give off. The problem is how much background there would be when you focus the light to a diffraction limited spot. But by using a near field probe and confining the light to a subwavelength spot, it became very easy to see the single molecules and actually image them on a substrate. And by virtue of the crazy shapes they made and changing the polarization of the light, you could determine the dipole orientation of every molecule. And furthermore, by fitting the known shapes of these spots, you could determine the positions of these molecules down about the 50th of the wavelength of light. So that was sort of the birth of single molecule biophysics, but it was within a couple of years supplanted by easier ways of seeing single molecules. The other influential experiment was when Harold, who was working on low temperature scanning microscopy, and I teamed together and we took his STM probe out and we put my near field probe in to do localized nanoscale spectroscopy of quantum wells, and so at 2 degrees Kelvin. And so with that, we excited through the near field probe, used the spectrometer, looked at the spectra of the emission from these multiple quantum well structures that were grown at Bell. And normally you would see this very broad spectrum if you used the diffraction limited spot. But instead we found that it would broke up into these very sharp lines. And furthermore, if you drove just a little bit, 100 nanometers away, this spectra would change completely. And so what we eventually came to realize was the light emission in these sandwiches, these semiconductor sandwiches, couldn't happen anywhere, but the excitons that were created would diffuse until they got trapped in some sort of little pothole from atomic roughness variations in the quantum well, and then they would spit out their photon with a wavelength based on the local thickness of that quantum well. So it's sort of like having a bunch of semiconductor molecules sprinkled through your sample. And so the thing that was key for us later on, there was a lot of physics that Harold was able to do with this, particularly since he was able to do a high magnetic field in his thing. I kind of nodded a lot during that part because I knew none of the condensed matter physics, but there was a lot that they got out of it. But what was important for us later on was to realize that even with that small near-field probe, there might be a dozen of these exciton recombination centers into the probe, and normally they'd be unresolvable. But because they glowed in different colors, we could isolate them in that higher dimensional space of wavelength and then study them one at a time. So this takes us up to 1994. I'd been doing near field for a dozen years, and I was thoroughly sick of it. By this time, because of our successes, it had become a hot field, and many, many people jumped into it. And if you know anything about the sociology of science, you'll know that many times we go through these boom-bust phases with different things, where the signal stays about the same, but the noise goes way up as a bunch of people who don't know what they're doing gets into it. And so they were claiming all sorts of crazy things at the same time that I was perfectly well aware of the limitations in near field. The primary limitation is that the near field is exceedingly short, and the light that comes out of that aperture spreads incredibly rapidly. So if you're even 25 nanometers away from your sample, then you have a significant loss of resolution. And it kind of made sense because the only samples I ever had any success with were ones that were ridiculously flat and where the thing you wanted to see was ridiculously close to the surface. What that meant is my dream of eventually looking at live cells was going to be a bust because cells are far rougher than 25 nanometers. And so that disappointment with the limitations of the technique, coupled with my frank disgust over what was happening in terms of the academic community with near field, I really felt like every good paper we published provided the justification for 100 pieces of crap that followed, and that every result, it was a waste of time and taxpayers' money. And I felt like my whole career had become a net negative to society. That was really my thinking at the time. And the final thing that was the sort of the straw that broke the camel's back was by '94, this was 10 years after the monopoly that the phone company was broken up, and it knocked out the financial underpinnings of Bell. And you could already see the beginnings of the decline of Bell, and they weren't going to be able to support basic research. But the final thing is that, yes, there were wonderful people at Bell, and I felt really inferior, and the only way I could feel like I belonged was by working my ass off. And the only guy I knew at Bell who worked even harder than I was Harold. And so we were best friends, but we were very competitive. So we would race in to see who would be the first guy in the parking lot every morning. And at 4:30, if I got in and I saw Harold's car in spot number 1, and I have to go to spot number 2, I'd get really pissed off, and then I'd put my hand on the hood of his car to feel by temperature by how many minutes he beat me by. And then he would do the same. And so, but we were best friends. We played tennis every morning. We'd ate dinner together every night. And it was a really great time at Bell, but it reached its end for me because of all of these changes. So in '89, we were these young and innocent guys, but the hard work coupled with that feeling of the weight of the world on our shoulders as Bell declined turned us in 5 years to looking like that. So that was reason enough to leave. So a few months later, as I'm trying to flush near field out of my head, and I'm unemployed because I really didn't know what I wanted to do next. I was basically a house husband. I was pushing my daughter around in a stroller, and I realized you could combine that single molecule experiment I did with the quantum well experiment that Harold and I did to make a new kind of microscope that would beat that diffraction limit. And so in this method, the idea is you have fluorescent molecules in your cell, and normally they just look like big fuzzy balls. And the fuzzy balls all run together, and you're kind of screwed at that point. But if those molecules are different from one another in some way, for example, if they glowed in different colors, then just as in that quantum well experiment, we could study them in this higher dimensional space of wavelength and isolate them there. Once they were isolated, we could fit the shape of that thing and statistically determine to high precision the center of that fuzzy ball. And hence we would know the location of every molecule to way less than the wavelength of light. And if we were able to strip these guys out all to be isolated, we would get then a super resolution map of the sample. So I was really proud of that idea for a month or so until I realized that the fly in the ointment is that in a biological sample there might be hundreds of molecules in one spot that's being illuminated at the same time. And so you would need a ridiculously good degree of separation, whether by color or whatever, to see one on top of 499 other guys. And there wasn't really a good way to do that. So I almost didn't publish this idea because, again, I was unemployed and kind of fed up. But if I hadn't, I probably wouldn't have gotten a Nobel Prize because that was one of the 2 papers the committee cited for giving it to me. It's still only been cited about 100 times in 20 years. So ultimately, I landed in my dad's machine tool company, which had been my backup plan all along. I worked on many things. My dad basically made these customized machine tools to make like brake calipers and exhaust manifolds and so forth for the auto industry. They would make machines the size of this stage in order to do that. I created a technology based on hydraulics, which was sort of a discarded old-fashioned technology, adapted it to nonlinear modern adaptive control algorithms and energy storage like you have in hybrid cars. And with that, I was able to collapse those machines to the size of like a VW Bug and make something that would machine much faster. It would move 4 tons at 8 Gs of acceleration and position it to a precision of 5 microns. I spent 4 years developing that, 3 years selling it, and in the end I sold 2 of them. And so I was not a very good scientist, but I was a really horrible businessman. And so after burning through about $1 million of my dad's money, I said, I'm sorry, and I quit, and I had no plan B again. And so that was the blackest time in my life, because not only had I pissed away my academic career, I had also blown up my backup plan of working for my dad. So at this point, I'm 42 years old. I have 2 small kids, and I'm unemployed and probably unemployable. So I did something smart, though, which is I contacted Harold. And Harold had left Bell in '97 and went to work for a company that works for test equipment for the disk drive industry. And he was considerably more successful there than I was, but he was feeling this dissatisfaction from being away from science. And so we started meeting together at various national parks and essentially nursed one another through our midlife crises. And what we came to realize is that while we were not really cut from an academic cloth, we really missed the ability to follow our curiosity and work in a lab and do science. We wanted to find a way to get back to that. So I started reading the scientific literature for the first time in 10 years, and one of the first things I ran across was green fluorescent protein. To me, this was almost a religious revelation, because it was so hard to do fluorescent labeling back in the near-field era. And the idea that you could snip a piece of DNA from a glowing jellyfish and splice it to the DNA of any protein in any organism that you want to see, and have that organism then express that protein so you could see it, was just crazy elegant as far as I was concerned. And I wanted to get back into microscopy. So I came up with an idea for a crazy microscope which would use different discrete beams from different directions to create an interference pattern that would create a 3D multifocal excitation field to do very fast 3D microscopy. This is based on optical lattices like the atomic molecular optical field uses, but a new class of lattices that I discovered by looking at the theory of it myself. And so that then brings us to when I've started to try to pitch this lattice idea to get back in the lab. The first guy, of course, I tried to convince was Harold. Harold was somewhat unconvinced, but Greg Bobinger, the head of the MagLab here, had been trying to recruit him, and on a previous trip, he met Mike Davidson, who we'll get to in a minute. And Mike works on live cell imaging, and Harold suggested that we go there together, and that maybe Mike would have the resources to allow us to collaborate and work on the lattice project. So we came here, and I did meet Mike. And I don't know how many of you know Mike, but he's an amazing man. He has been working here for many years as a microscopist. He, at one time with polarized light microscope, put cocktail mixes under there, took pictures of what the cocktail mixes looked like, imprinted those on neckties and sold those and made a lot of money. And then he was able to use that money to then start working on the development of one of the most amazing websites ever. Huge educational website, everything you want to know about microscopes, but we're afraid to ask. It gets an amazing number of hits even today, and it's the go-to resource for anybody who wants to learn about microscopes, from the very basic to the most advanced. And eventually he started then doing the tutorial sites for 3 of the 4 major microscope companies. In order to do that, you want to be able to sell these microscopes, you want to sell their ability to look at live cells. So Mike is a world expert on live cell imaging. And since the advent of GFP, that means being an expert on fluorescent proteins. So Mike has one of the world's largest libraries of fluorescent protein fusions, created all here at Florida State, done to a large degree by him recruiting undergrads at FSU, many of them who had less than stellar GPAs, and helped turning them around to do productive research in his lab to create this library. So it was from Mike that we learned that there weren't just fluorescent proteins, but there was a new thing on the scene called a photoactivated fluorescent protein. So instead of shining blue light on these guys and then they glow green, if first you shine blue light on them, nothing happens. But if you shine violet light on them first, then they're activated, and then you can shine blue light on them and they'll glow green. And so Harold and I, when we flew in this morning to the Tallahassee airport, felt very nostalgic, because 9 years and 11 months ago, we were leaving the Tallahassee airport after that visit with Mike, and we were sitting there, and it struck us by hearing about these photoactivated fluorescent proteins that was the missing link to make that idea that I had pitched in my first round of unemployment to work. So the idea is you have your cell, you make it so that you coax it to express the protein you care about with a photoactivated fluorescent protein fusion tag. And you turn on the violet light so low that statistically only a few molecules come on at a time. And then they're isolated from one another, and you can find the centers of their fuzzy balls, like over here, and then you plot those positions. If instead you sum the fuzzy balls, you get a diffraction-limited image. But if you plot the centers, you get what's called photoactivated localization microscopy, or palm image. So it's the idea I had in '95, but with time instead of wavelength is the way of separating this. And it seemed like it would be ridiculously easy. So we were very scared, Harold and I. I had convinced Harold to basically quit his job a few months before, although I still hadn't sold him on the lattice idea. And so we have a really great idea, but we have the basic problem that we're both unemployed. But the good news is that Harold doesn't burn his bridges as effectively as I do. So when he left Bell, he was able to take a lot of his equipment with him. So we pulled that out of the storage shed, put $25,000 each of our own money for things that didn't exist 10 years previously. And it was just going to take way too long to get funding to do this any other way, other than by ourselves. And normally you would do it in the garage, but we were able to do it in the living room because he wasn't married at the time. So it was easy to set up there. And then we had our microscope built. We came here in April of 2005. We submitted a patent in May 2005. We had this thing built probably by the end of August 2005. But we had a problem in that we were two physicists who knew zero about biology. But one of the places I was scheduled to go to try to sell my lattice idea was National Institutes of Health, where I begged to meet Jennifer Lippincott-Schwartz and George Patterson, who were the inventors of the first of those photoactivated fluorescent proteins. So I took them to lunch, swore them to secrecy, told them Harold's and my idea, and Jennifer said, "That sounds fantastic, bring it here and we'll give it a try." And so in early October, we shipped it over to NIH, and probably by the end of the month, or early November, we were starting to get data. So this is now a thin section cut through a cell, looking at something called multivesicular bodies with a marker of the membranes. Turning on the violet light so low, you see the single molecules. If you sum the frames, you get the diffraction limit image. If you start instead finding the centers and plotting those, you build up the palm image. And after 20,000 frames of doing that, much of the time Harold and I taking turns sleeping on the concrete floor of the darkroom, which is probably about 35 degrees Fahrenheit much of the time. You go from this to this, or in the end from this to this. So with a well enough labeled sample, you can go from the 200 nanometer diffraction limited resolution limit of a standard microscope to 10 to 20 nanometers by the palm technique with something simple enough to do in your garage. So 2005 was the luckiest year of my life, because not only did I get to reconnect with Harold, not only did we get to do what was probably the funnest thing he and I will ever do in our entire lives, which was to build that microscope, win, lose, or draw in the end, but actually win and have it work. I also got connected by various Bell Labs connections to the Howard Hughes Medical Institute, which I had never heard of before, but is actually the second biggest medical philanthropy in the U.S. after the Gates Foundation. Today, our endowment is $19 billion. They were interested at that time in building a biological Bell Labs. Harold and I were homeless, and that sounded like the dream home. And that's exactly what it's turned out to be. So Harold and I went there. For 2006 to 2008, I lived and breathed Palm. Harold will tell you his story there. We were able to do many, many different applications. I'll skip over that in the interest of time. But basically, that whole stuff basically led to, less than 10 years later, essentially going to Stockholm and getting the prize. And the bittersweet thing about winning that prize is that you can only have 3, and Harold was left out. And I really view this prize as much as his as it is mine. There is no way I would have had the courage to do the Palm without him by my side. So I really feel that he has as big a piece of this as I do. So my final slide then is, I feel like a hypocrite for accepting the Nobel Prize because I've always felt like, the accolades are subjective, but the accomplishments are objective. The accomplishments were what we were able to do in that living room. That's what I'll remember on my deathbed, not what the hell happened in Stockholm. That's just the opinion of 6 guys, and everybody can have a different opinion, okay? So, but if you're the type who cares about how to win a Nobel Prize, I think I've discovered the winning formula on how to do this. In 1986, Harold published by himself a paper on an idea called evaporative cooling, which was then a way to get around the bottleneck for how cold you could get atoms to go from millikelvin to microkelvin and beyond. That idea was then taken up by Cornell and Wieman, and they were the first to then generate a Bose-Einstein condensate, for which they won the Nobel Prize in 2001 using Harold's idea. In 1989, Harold was then at Bell Labs when he studied type 2 superconductors with scanning tunneling spectroscopy, and he discovered a previously unknown core state at the center of this Abrikosov flux lattice. In 2003, Abrikosov won the Nobel Prize in Physics. In 1994, Harold and I did that quantum well experiment that sparked the idea for the paper I wrote in 95 that would become Palm. In 2006, we used his brain in his living room in order to be able to actually demonstrate Palm, which led to my getting the prize in 2014. So if you want to win a Nobel Prize, just stick close to Harold and it's bound to happen. Thank you very much.